Okay, this is Specialist Maths 2020, Paper 2, Tech Active. This video is for that last question, question 19. And it is a doozy, isn't it? I'm assuming you've all read it. So an object is swinging at the end of a 0.5 metre length of string in a vertical circular path with a constant angular speed, completing each revolution in 0.24 seconds. The object is projected from a height of 0.3 metres above the ground in a vertical plane, just passes over a narrow pole shown in the diagram. The pole is 2.05 metres high and its base is 14 metres horizontally from where the object was projected. Then there's the flat top vehicle with a length of 0.6 and a height of 0.4. Initially at rest against the pole, as shown in the diagram. I've lost where I was reading. At the instant of the object is projected, the vehicle moves in a horizontal direction away from the pole in the same vertical plane as the acceleration of magnitude A. The object strikes the middle of the vehicle, of the top of the vehicle, assuming that the air resistance is negligible. Use vector calculus to model the motion of the projectile in order to determine the value of A. Wow, there's a lot of things going on here. Sorry I'm a bit shadowy, but that's where we're at. So here we've got circular motion, we have projectile motion, and then we have this accelerating. It's going to land in the middle of that. Now I'm assuming my origin's here, so I can see that it's being projected at 0.3. That's where it's being projected from, the position. It's going to go up over. It just misses this point, which will be 14, 2.05. And we've got to work out where it's landing. It's going to land in the middle of this trolley, but this trolley is actually moving that way with acceleration equaling to A meters per second squared. So, as I said, a lot happening in this question, and so you need to break it up. Now, doing the obvious, that's I direction, that's J direction. So horizontally is I, vertically is J. So we've got this, it's a big projectile motion question, but what's happening here initially, we've got that circular motion. Now we're told that that completes each revolution at 0.24 seconds. 0.24 seconds there. So that's my period. So my angular velocity is 2 pi over 2.4. Let me just do that on my calculator. 2 times pi divided by 0.24. Let's work in decimals. Gives me 26.18 radians per second. Now we know V equals R omega. Okay? Is that one on the rule sheet? I can't remember off the top of my head. Now, what is the radius of our circle? Our radius is 0.5. So that's 0.5 times 26.18. So, move that down, times 0.5. Oh, hang on, syntax error. Shift, answer. We get V equals 13.09 meters per second. So with our projectile motion, that 13.09 is our speed it's initially being projected at. Now, we've got gravity. Let's approach it like a regular, I'm going to go to another piece of paper. Sorry about that, people. Regular projectile motion, acceleration is negative 9.8 J. So obviously then to go to velocity, we integrate, we get negative 9.8 TJ plus C. Now, my initial velocity is going to be, my VO is going to be 13.09 cos theta I plus 13.09 sine theta J. Because we know it's being projected at 13.09 meters per second, but we don't know at what angle it's being projected. So that's something that will come out as we work through this. All right, so we've got to find C. So at t equals 0, it equals that. So 13.09 cos theta I plus 13.09 sine theta J equals, well, that's negative 90 plus C. So that's my C. You can show the working. I think you've probably done enough projectile motions that you automatically run through with this, don't you? So V equals, adding that in as my C into this, 13.09 cos theta I plus 13.09 sine theta minus 9.8 TJ. So therefore, I'm getting onto my projectile motion, aren't I? Working my way through. I'm then going to go to my position. So from there to there, I integrate. I'm going to integrate again. Oops. To get my position vector, R. So that's going to be 13.09 cos theta Ti plus 13.09 sine theta T minus 4.9 T squared J plus C. So I'm just integrating. Remember 9.8 T squared over 2, so that's where I get my 4.9 from. Now, initial position, I want to find C. When T equals 0, R equaled, remember, let's go back and look at our picture. R was this initial position, 0 and then 0.3. So essentially 0.3 J. So 0.3 J. Now that's going to go to 0. I'm going to have 0 I. It's going to be 0 minus 0 J plus C. So that's my C value. So then we're going to get to, and we're going to go R equals 13.09 cos theta Ti plus, I'm going to put the C in because so I'm going to have 13.09 sine theta T minus 4.9 T squared plus 0.3. That's my J. So I have my position vector happening now. So we've got in T and we've got theta of where we're going with that. We know a few things about our position vector. It goes and we're going to go and that's our point there, isn't it? So I'm going to go back and put this in parametric form. So X moving along is going to be my 13.09 cos theta, cos theta T, and my Y is going to be 13.09 sine theta T minus 4.9 T squared plus 0.3. What I want to do is create a Cartesian equation that maps this projectile motion. So that's where I'm going here, going with my parametric form. I want in X's and Y's so I can get a Cartesian. So going to Cartesian, I'm going to change this to t is x over 13.09 cos theta. Sub it across. I'm going to get y equals 13.09 sine theta t. Oh, sorry, I'm not going to have t. Apologise. Substituting for my t is x over 13.09 cos theta. Plus take away 4.9 x over 13.09 cos theta, that's squared, plus 0.3. I didn't really leave myself enough room to write that. Simplifying this up a little, I'm just going to move it down here a bit. Y equals, the 13.09s will cancel. Sine over cos obviously is going to give me tan. So tan theta x minus 4.9 x squared over, let's just go 13.09 cos theta squared plus 0.3. So we get to that point and we've got a Cartesian equation. So for that Cartesian equation, we're missing our theta, but we do know that this projectile motion goes through this point, 14.205. So that's my point I'm going to put in. So I'm going to sub in 14.205. So that's 2.05 tan theta times 14 takes 4.9 14 squared over 13.09 cos theta squared plus 0.3. We want to solve this for theta, don't we? So let's go to my calculator. I'm going to do options, calculate, solve n. Oops, hang on, get down the right spot. Solve n. 2.05 shift equals tan theta times 14, take away 4.9 times 14 squared over, and it's okay that it's over, just one part of it, doesn't matter, 13.09 squared, and cos x, close bracket, squared, plus 0.3. Close my brackets. It's a big one. Let's see what it comes up with. It's thinking, exit. Let's go up and scoot across. We want a positive angle, don't we? I'm in radians working this out. There we go. Theta equals 0.644 radians is my angle. So we're working through, I've got my angle. So, sorry, I'm not my friend. So we've done our circular motion. We've got our Cartesian form of our projectile motion. We're trying to work out the landing. So we're into the third part of this question. Now we know that, I've got all my bits of paper, sorry about that. Let's call where it lands. So this point where it lands, I don't know what the x value will be, because remember this is moving, but I know it will be 0.4 high. All right, so I don't know the x value, but I do know it's going to be 0.4 high. Oops, sorry, I'm just shuffling my papers. So what we're going to do, looking at my Cartesian form here, so I'm going to rewrite that as y equals tan 0.644 times 14, take 4.9 14 squared over 13.09 squared cos 0.644 squared plus 0.3. Obviously, you could simplify these numbers for your working. Not a problem, we can do that. Now we're looking at the point B, 0.4. So we essentially want to know how far over is this going to land in the X direction. So if I go 0.4 equals tan 0.644 times 14 minus oh shoot, sorry, I made a little error there, didn't I? Apologies, I didn't go to my Cartesian, didn't I? I should have had x and then x squared. Apologies, so that should be my x. So that's my x minus 4.9 x squared over 13.09 squared cos squared 0.644 plus 0.3. I know I made an error, but I'm not going back to the start of this video because it took too long to do. So this was the one, oops, I was wanting, and I accidentally looked on the one below with the 14s, didn't I? Made that mistake. I want to solve for x. So my x is actually my b. So let's go solve n. Solve n. Oops. 0.4. Shift equals, can you see this? Tan 0.644, close brackets, times 14, take, oh man, no, I did it again, didn't I? Delete, 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 times x. Take 4.9 x squared over, in brackets, 13.09 squared, cos 6.44, close bracket, squared, plus 0.3, oh, didn't do my bracket, did I? But, oh, it did it for me anyway. Hang on, I think I've made an error in where I'm going here. So let's try that again. Just going to try that one more time. Sorry guys, I think I just, what am I going to do? I was going to delete all. Let's start again because I think I went astray. Oops. So 0.4, oh, delete. Options, calc, solve n, 0.4, shift equals tan in brackets 0.644 times x minus 4.9 x squared over, I might just do it as 13.09 cos 0.644, close brackets, squared, plus 0.3, close brackets equals, exit, that's the answer I wanted. Now we come out with two answers. We get x equals 0.13, we get x equals 16.66. If we look at our diagram, our point over here is beyond 14 metres, so therefore it must be this one, because x must be bigger than or equal to 14. So 16.66 is our landing spot. And that's where we're impact. So our impact on our trolley is 16.66, 0.4. Now we know that this trolley is moving with a constant acceleration. So we need to work out where. So I'm going to work out time of flight. Now, if we go back to our parametric equations, I'm just going back up to here, that we had, I can go T equals 16.66 over 13.09 cos 0.644. Okay, so just put that in there. So go down here, I'm going to go 16.66 over 13.09 times cos, 0.644, close my brackets, execute, and I get 1.59 seconds is my time of flight. Okay, that's going to be important for us. Let's look at the motion of the trolley. Or motion of the trolley or motion of the cart. It's straight line motion, isn't it? And we know that the acceleration is A only in the I direction. So V will be ATI plus C. Now, if we want to find C, the velocity at time equals 0. This cart starts here. At time 0, it's motionless. Okay? So at T equals 0, V equals 0. So therefore, C equals 0. So V equals ATI. We want to go to position. So then let's go to R. Integrate again. AT squared on 2I plus C. What was it? Its initial position. So we want to find C again. At time equals 0, R equals 14.3I. Remembering initially we're talking about the middle of the trolley. So easy mistake is just to say 14, but we actually want to the middle of the trolley, so that's 14.3. So 14.3I equals, that's 0I plus C. So that's my C value. R equals AT squared on 2 plus 14.3 I. Okay, we know the time. I'm going to go another bit of paper just to give myself some room because I'm getting a bit squishy. So we know at time equals 1.59, because remember we walked out time of flight. The R position is 16.66 I, because that's where it's landed. So we're nearly at the end here, so we're going to have 16.66 equals A 1.59 squared over 2 plus 14.3. Let's solve it N, and that should be able to give us our A value. I'm just going to delete all, just so I've got a nice clear screen for you. So I'm going to go to Calc, solve N, 16.66, shift equals my X bracket, 1.59 close bracket squared over 2 plus 14.3, close my brackets, and we get A equals 1.867 or 1.87 meters per second squared. So that is my acceleration, the acceleration of that trolley. It's a monster question. There's so much. There's a circular motion, the projectile motion, you're finding time, you're finding the angle, and then finally you're finding with that going and you find A. It's acceleration. Whew, thanks.